I guess contrary to previous speakers, I will be less formal, and I hope I will be a little bit more practical. No offense, guys. I'll be talking about performance analysis and also about finding performance bugs and performance changes like degradations and optimizations in general. Now, finding performance bugs is very hard because they tend to manifest with a big workloads or inputs only. And obviously, if you have a too big workload, the testing itself will be time-consuming. So this could make the performance quality assurance a hell, literally. Yeah. And obviously, we could use the static analysis. However, in my experience, the current state of the performance static analysis is inapplicable in practice and insufficient. And yet, performance degradations usually have a huge consequences, especially in a critical software, like in your case in kernel, right? Moreover, the performance bugs are pervasive in today's software. I can cite, for example, the famous inefficient white space trimming regular expression, which made Stack Overflow unusable for several days. And I think that all of you use Stack Overflow every day, right? So imagine you cannot work with Stack Overflow for a day. Hell, right? And there are some other bugs like in Rust, in MongoDB, in Vim, Chromium, Ruby, and many others, which are, for example, documented by a very good accidentally quadratic block. So obviously, you could manage the performance of your application yourself. However, this is also a very tedious job because you have to maintain the context of your performance profiles. You also require some degree of automation for your profiling, detection, etc. And also, the most necessary, you need to preserve the history of the performance. So today, I will introduce you Perun, the performance under control. Perun is the very first open source lightweight performance version system. I'm saying very first because I invented the term performance version system. So to my best knowledge, this is the very first, right? And it is written in Python, my favorite language, even though it is not as performance, well, friendly, I guess. So what is Perun? Perun is basically a wrapper over existing version control systems, as well as a performance tool suite, which provides the context of the profiles. It provides a certain degree of automation for the collection of the data, for post-processing, for detection of changes, etc. I hope it is kind of generic, so it can serve as a platform for creating new kinds of profilers or detection techniques, models, and many other. And I hope that it is easy to use. I really hope. Yeah, even though sometimes I curse myself a lot. So on one side, you have the functionality in version control systems, your code changes, and next to it, you have a Perun, and you have a performance profile statistic visualization interpretation. Now, the main part of every performance analysis is the collection of data. In Perun, we have a oh, Jesus Christ. I have no idea what I did. OK, cool. So instead of the light, whatever. So we have three collectors of runtimes over functions, in particular the complexity, tracer, and time. The most notable one is the tracer, which is based on system type. I think that a lot of Red Hat guys are familiar with this system type, which supports also some dynamic and static probes as well as we can measure cache hits and cache misses. We also have some very simple memory collector. However, in my experience, there is no memory collector which scales very well in practice. So it is, to be frank, unusable. And very recently, I've created a wrapper over a static analyzer Lupus, which can collect the bounds for integer loops and, to some extent, to heap manipulating loops. So we can also infer the complexity of loops. Now, based on these profiles, there is a very main feature of Perun, and this is the automatic detection of performance changes. So imagine this scenario. So you're a user, you create a set of changes, you commit them, and you create basically a new version, new head. Now in Perun, we trigger new collection of data for certain test scenarios. You collect raw data, you post-process them, you create a set of performance profiles, which we tend to call the target profiles. So this is something that we want to analyze. However, just the target profiles alone are insufficient to say that there is a degradation. So we look into a history, and we extract so-called baseline profiles. So this is basically the performance expectation, something that we will be comparing the new version against. And we feed them to some kind of oracle, let's say, which will tell us whether there is a degradation or optimization with a certain degree of confidence. However, I have to stress that this is dynamic analysis, so we cannot prove that the degradation is there, simply that there is possibly some degradation. So what would I like you to remember about Perun? Perun is a wrapper over existing repositories, it is a performance tool suite, and it is a performance profile storage. And with it, you can collect performance data, you can interpret some performance models and some results, and to some extent, you can detect performance changes. However, this is not the end of my talk. In the rest of my time, hopefully, I will present the 3 short studies, how we used Perun on some practical, hopefully practical projects. I have named each one of them after a book of my favorite author, and I hope that they will be self-explaining. So the first case is called After the Funeral. So imagine there is a dead body in our project. We know that we have already dug up the performance bug. So we want to do some kind of proof of concept that we can use Perun to find existing performance bugs. So let me tell you a story of the ctags utility. Ctags, maybe you know it, can be used to generate an index of symbols in your source code. So you have a lot of headers, a lot of sources, and you pre-generate some kind of index called a tag list, and editors can then load it and speed up the lookup. But good guys in Vim noticed that sometimes users merge several of these tag lists together, and this led to a duplicate results when you did a lookup of the tag. So they decided to deduplicate this. However, they stored the results in array. This means that when you looked up some tag, this is itself a linear function, and you found a match, you then traverse the array of matches again, which is linear again. So basically, this is accidentally quadratic solution. Obviously, this went unnoticed for some time until some user had a very huge tag list. And he complained that there is a huge slow up, that everything sucks, simply. And he obviously proposed some fix. He's changed, basically, the array for hash table. And it was resolved. Now, the funny thing is that some other user reported this bug as well. However, he instead proposed a workaround that was simply waiting for Control-C, and then it aborted the lookup and returned the power to the user. So it didn't fix anything, but at least you didn't have to, plug off your computer to end it. So obviously the question is, can we find this bug using Perun? So this is a joint work with Szymon Stupinski. We chose 2 versions, the one where the bug was reported and the one where it was resolved as a target and baseline version. We used tracer to collect the runtime of the functions. And for the collected data, we generated 4 kinds of models, 3 non-parametric and 1 parametric. Now, non-parametric means that the model doesn't depend on any independent variable, only on the number of collected resources. In parametric, we require some kind of independent variable. I will show you the examples of these errors on the next slide. Then we used 2 detection methods. The first one is based on computing integrals. The other is based on some local statistics. I will not go into any details, that you know that we used some kinds of detection techniques. Now, to show you the illustration of the models. Now, the red dots are the individual runtimes of the function. This is the regressogram, which basically breaks the dataset into subintervals. For each subinterval, it computes average or median or something, and it outputs the step function. So I hope you can at least see a little bit of the model. This is basically a step function, very coarse representation of the data. Now, more elaborate is the moving average, which basically takes a sliding window and moves through the dataset, computing the average or mean. I won't tell you how kernel regression works. It is much smoother, but it is very, very, very complex. And the last one is the regression analysis. This is classical mathematical method called least squares, which we use to infer for example, quadratic models, logarithmic, linear, and so on. So this is just comparison. I hope you can see that the regressogram has the least fit, while the regression analysis and the kernel regression best fit the data. So we tested some very simple scenario. We pre-generated some tag list, then run the vim, try to find a tag, and end. And here I report only the 3 most affected functions. And I hope you can see that using all of 4 models and both of the detection methods, we can find a degradation up to 100% increase. Now, in brackets, there is the confidence rate, which is basically the coefficient of determination, which tells us how well the models fit the data. So this is our confidence. So if the confidence is high, then probably the bug is, in our opinion, not spurious. Now, in follow-up experiments, we verified that this bug was not reintroduced, and we didn't find any degradations for this scenario in Vim anymore. Now, the second case is called murder is easy. So I said that it's hard to find a good workload. So can we find something automatically that would kill our software? Again, I will start with a little story. So there is a common evil pattern in regular expressions that can form the regular expression denial of service. This was found, for example, in the email validation regular expression that was available publicly from some regular expression library. So some basic user could simply find it, even non-basic, copy-paste it to his application, and introduce a vulnerability. I won't go through the regular expression because it's complex, and in my opinion, it's actually not email validation regex at all. But I highlighted the evil pattern. The issue is that there are nested repetitions in the regular expression, which, if translated to non-deterministic automaton, will lead to a kind of butterfly loop. I highlighted the butterfly loop by red. This is not a problem if you have a matching case. It matches the words and ends. But if we have a non-matching case, we have to explore all of the possible paths in the automaton, which means we have to explore all of the interleaving of these loops, these 2 branches, which leads to an excessive number of non-matching words, and this is the source of the denial of service. So I propose to use fuzz testing. If you're not familiar with fuzz testing, it is an automatic test, basically automatic testing with randomized or mutated inputs. You feed it to your program, and you look for crashes or leaks and stuff like that. It's not exactly focused on performance at all. There exists a solution called Fuzz, but it has limitations. It uses the classical AFL rules, so flipping bits and bit stuff, basically. And it uses the code coverage as an evaluation function, which doesn't necessarily say that there is a degradation in your code just because you have bigger coverage, right? So we got inspired by existing performance bugs, and we devised a new set of rules for mutations that are, for example, for text file, we double the size of the line. Now, this is inspired by a particular issue in gedit, when you had an even small file with a long line, and this led to a very slow response of the editor. So it makes sense to have a finely tuned rules for fuzzing. So together with Matusz, we created the Perun Fuzz, which is a mutation-based fuzzer with 2 evaluation fitness functions. The first is correlation-based. This is the same as the Perf Fuzz. It is very fast heuristic in our experience. And the other is we simply run Perun over the new mutations and compare them with the baseline. So we have a loop. We have some initial seeds. We compute baseline profiles for them. Then we mutate. For the mutation, we compute the target profiles. We compare them. If we find degradation, well, then it's obviously an interesting workload, and we can kill our application with it. So I will show you some results. This is for the evil regular expression. We started with some valid email address of 18 bytes. And after several applications of rules, we got string of the same size, which led to a degradation of 1 order of magnitude. We then tried several more. We ran the fuzzing for more hours, and eventually we found this horrible monster that has 36 bytes, and we had to kill the program because it ran for over 5 hours and it didn't end it. So we can find even such a horrible, extreme workloads as well. Now, the last case study is called the destination unknown. So let's say we have some project and we want to do some deep profiling. We want to find something, anything. We want to use the classical interpretations in Perun. So once we got a codec for the CCSDS format called Open122, and this codec, it takes a picture with one potentially infinite dimension. It works in 2 steps. First, it does a discrete wavelet transformation. I believe that the transformation basically takes a picture, it upscales it, passes it to some high-pass filters. This creates some kind of brightnesses. Then you combine this picture and downscale the picture. Well, it's complex. I hope that you can at least remember something from this picture. But it does, well, some transformation. And this is followed by bitplane encoding, which basically shrinks the image. I mean, the data. Now, both of these phases should work in linear time regarding the image size. So we try to measure the runtime, cache hits, cache misses. We try to scale by height, by width, by image size, and we got some interesting findings. Now, this is the first one. So we compared the runtime of the decoding function for the bitplane encoding with the number of cache misses in L1D cache. And we scaled the height of the picture. So on these 2 pictures, on the x-axis, we have the height of the input picture, so they are more heighter, I guess. Higher, yeah, thanks. And on a y-axis, we either have the runtime of the decoding function or we have the number of cache misses in millions. Now you can see these are generated by Perun using the bokeh library, which is very nice, but that's on scale. And you can see that there is some breaking point in the data, which should roughly correspond to the size of the L1D cache, where the number of cache misses in L1D rises considerably. And this obviously affects the decoding function, which is shown in the very screwed up runtime of the decode function. This is the first finding. The other interesting finding are these DNA-like patterns, or I thought of it in a different way, but I'm from Ostrava, so you can imagine, yeah. And we are actually unsure what these patterns are and why they are introduced in the data. Now, the codec itself has three options, the DVT1, DVT2, and DV2MS. It can either have 0, 1, or 2. So these are basically 27 configurations of the codec. We tried them all. Again, we measured a lot of data. And in this table, I list the slope of the linear model of the cache cache misses in L1 cache above and below LL cache. We tried scale by height and by width. And you can see that if we scale the pictures by width, all of the configurations, they behave, the cache misses behave quite stably, quite good, which is why they are green. If we scale by height, we got a at least twice as big slope in the cache misses. So it is better to scale the pictures by width instead of height. This is first finding. The other interesting finding is that we can see that in the first column, this is the case when we scale by height and we set the DVD-MS option to 0. The cache misses are the worst. So there are most cache misses if we use the DVT-MS equal to 0, which was confirmed to us by the author of the codec who said that the 000 is the suboptimal mode and 222 is the best mode. So now, to sum it up, I showed you that Perun can be used to find performance changes, to find time-consuming workloads, and to perform some deep profiling. Now, there are a lot of follow-up works that we are currently exploring, or we would like to explore in the future. In the near future, we will revive the graphical user interface for Perun, and also we are currently optimizing Perun itself, because, for example, the collection of data is still not usable on very big projects, because even for the Vim, we generated profiles of several gigabytes, so unfortunately. So we are trying some optimization techniques. And I conclude with some acknowledgements in pseudo-random order. I thank all of the people here who contributed to Perun, either by financially, visionary, or by anything. So thank you very much for your time, and I will answer any questions.
Thank you. So we have time for questions. At the back. Okay.
So I've excuse me, I've written my own analysis tools like these, and the problem there, and to some extent you worked around this by selecting appropriate test cases there, is that the amount of change you can actually verify to be there for every single change, or even a collection of changes, is usually dwarfed by the noise of the measurements which you're actually doing. So in your cases, you have mostly concentrated yourself on having asymptotically worse results which you measure, which you can see. So I see that as something, but in practicality, what we would need is something which can actually have all kinds of performance regressions as small ones, because small ones, many small ones, over hundreds of iterations of patches and so on, will accumulate over time. But you want to actually find out where it actually starts and what are the contributing factors there. So for that, what you will need, and which I would have missed, at least in the slides, maybe you have done this there, is that you always have to have some form of error computation along with the measurements there. So at any point in time, you run the whole thing multiple times, and you have to say, well, yeah, my measurement error is in this area. And my found out, for instance, you're doing linear regression basically on the curves for curve fitting or something like this. Is my slope basically so larger than the amount of error which I have there? So this has to be part of the analysis, but also part of the report. Are you actually doing this?
Actually, no, but it is a very interesting suggestion, and I'll definitely explore how to.
That's really absolutely crucial in this sense. So I've done my own tools based on these kind of ideas in the past, but for pretty much all the code which I have verified there, basically, the amount of error of even, let's say, 10 of the iterations of the patches and so on is dwarfed by the error of the measurements. So the only thing where I was able to do some actually have some good results is if I ran this through my simulator, so an assembly simulator, a CPU simulator, which got out the noise of the system, but that's not really practical.
Yeah, I agree with you. And like I said, that there are still issues. One thing is that this is dynamic analysis, so we have to run the program itself to collect the data. So if someone starts downloading some torrents or something like that, or even if the system starts updating, it will obviously skew our data.
It doesn't really need the interference of another process. The randomness in the execution on a single CPU when it comes to the internal factors of how the CPU is implemented, the various queues with the amount of how the memory is laid out and so on. This is introducing so much noise for the amount of work which you can actually measure there realistically, especially if you're looking at the scope of an individual function. Oftentimes you really cannot get a signal because the signal you're getting is smaller than the error measurement.
Yeah, I want to maybe note that one of the follow-up work that we would like to explore is some statistical post-processing of the data that we collected. So try to, for example, remove the outliers from the measurement data. I know that this probably will not help at all. But, we have a lot of this is mostly work of students, so we can like try out stuff that may not work at all.
But there's more. So the thing which, so Sanjay is not here right now, so the thing which we have been working on is actually having statistical modeling of the error of the noise.
Yep.
So if you can do that, then you potentially, so if you can model the noise, what you can expect, you can basically subtract that from the range of the values which you're getting, and then again, you can perhaps get a much more precise thing. But then it gets completely complicated, and you have to do a lot more. So you cannot just look at the function set black boxes. You actually have to model the expectancy, the expected error of the instruction sequences and so on. So having this as this black box is useful for asymptotically wrong algorithms at algorithm level. So if you would rename your algorithm, so the whole thing a little bit to put in algorithmic changes, then I would be fine with this. Yeah. But it's not performance as per se, because that gets more complicated, and we can talk about this. So we have done lots of work on that.
Yeah, okay, thank you.